Let us consider the no load transformer. So if this is the flux phi, voltage V1 will be like this, that is flux will be in exactly 90 degrees lag with the input voltage V1. And if suppose this is the induced voltage E1, that is of primary winding, and let this be the induced voltage in secondary winding, that is E2. As we know that the permeability will vary with excitation, therefore current will not be in phase with the flux phi. Let the no load current be I0. So this is the I0, and as now here I0 can be resolved into two components. One component along with flux called as magnetizing component, and the other component of current which is along with the input voltage is called core loss component or working loss component. Let us suppose the angular difference between the input voltage and no load current be phi naught. Therefore Imu is equal to I naught sine phi naught, and IW or can be represented with IC, which is equal to I naught cos phi naught. Imu will be 4 to 5% of full load current, and working loss component will be, that is working loss current will be 1 to 2% of full load current. Now let's study about the operation of transformer on load. Here we will come across the important concept like why transformer is a constant core flux device and why transformer is called as negative feedback circuit. Now let's see that. If suppose this is the input voltage applied to the primary winding of transformer, and as primary winding is closed circuit, so current will flow, and let that primary current be I1, and as current flows in the primary winding, then there will be flux phi1 which is of alternating nature, because here input voltage is of alternating nature, and according to the Faraday's law of electromagnetic induction, as this is the stationary conductor and the flux is alternating, so there will be an EMF induced in primary winding. That induced EMF we are representing with E1, which is equal to N1 d phi1 by dt, where N1 represents the primary number of turns, and as this flux phi1 links with the secondary winding of transformer, then there is an EMF induced in the secondary winding of transformer, which we represented with E2, which is equal to N2 d phi1 by dt. And now as the load is connected, there is a current flowing in the secondary winding of transformer, let that be I2. Now as current is flowing in the secondary winding of transformer, then there will be flux phi2, and that flux phi2 will flow towards this direction, that is opposite to the primary flux. Please keep in mind that windings ought to be wound like this, that is phi1 and phi2 direction must be opposite to each other. As now flux phi2 is opposing the flux phi1, then there is a decrease in the flux phi1, which will obviously decrease the induced EMF E1, but to maintain E1, transformer will drag more input current from the input supply, and that extra current which is drawn from the input supply to maintain E1 is represented with I2 dash, that is I1 is equal to no load current plus I2 dash, because without load there is a current in primary winding, that is I0, and because of placing load there is an extra current which is I2 dash, and together we are representing with I1. And now because of this extra I2 dash, there is a flux phi2 dash, which is equal and opposite to that of phi2. As phi2 dash and phi2 are equal and opposite to each other, they both get cancelled, and the flux only that remain in the core is phi1. So is why transformer is said to be the constant core flux device. So whatever the load that you place, according to that there will be flux phi2, and according to that the transformer will drag extra current from the input supply, so that there is a flux phi2 dash. As phi2 and phi2 dash are equal and opposite to each other, they both get cancelled, and the flux only that remain in the core is phi1. So irrespective of load, the flux in the transformer core is constant. So is why transformer is said to be a constant core flux device. And it is discussed that I0 is having two components, that is magnetizing current and core loss component current. Magnetizing current is for flux and core loss component is for supplying the core losses of the transformer. Let us consider the step down transformer, and if suppose this is the input supply current I1, as I1 is having two currents I0 and I2 dash. This is I0 and this is I2 dash, and further I0 is having two currents IMU and IC, therefore it is subdivided into IMU and IC. And from the phasor diagram, if you observe that IMU is in phase with flux phi and IC is in phase with V. Therefore this is the schematic diagram of the actual transformer, and of this schematic diagram, this represents the ideal transformer schematic diagram, and the whole together represents the schematic diagram of actual transformer. Let us finish this circuit with load, because if there is a load, then only there will be current I2 dash. If there is no load, there will be no current I2 dash. So from this discussion, you must understand that irrespective of load, transformer is a constant core flux device. And now let's understand why it is also called as negative feedback circuit. We know that if this is the input signal, and let this be the system transfer function, and let this be the output signal. If output signal is fed back to the input signal, and if the feedback signal is decreasing the input, then that type of system is called as negative feedback circuit. And if the feedback signal is aiding the input, then that type of system is called as positive feedback system. And coming to the case of transformer, observe that input here is flux phi 1 and output flux is phi 2, and flux phi 2 is fed back to the input, and as flux phi 2 is decreasing the flux phi 1, so is why this system comes under negative feedback circuit. Therefore transformer can also be called as negative feedback circuit. Now let us consider the resistive load case, which means here the output voltage V2 and current I2 will be in phase with each other. So we know that in phasor diagram, if suppose this is the transformer flux, and we know that this is the input voltage V1, and why flux is in exactly 90 degrees lag with input voltage means the primary winding is of inductive nature. This will be the induced voltage E1 in the primary winding, this will be the induced voltage E2 in the secondary winding, because transformer provides 180 degrees phase shift. So is why E1 and E2 will be in exactly 180 degrees phase displacement with V1. And in ideal transformer, we seen that the no load current I0 will be in phase with phi, because their permeability is assumed constant. But in reality, with excitation, permeability will vary. So is why current will not be in phase with flux phi, and that current we represented it I0, that is no load current I0, and here load is placed, so there will be extra current I2 dash, therefore there will be resultant current I1. So as here resistive load is connected, so I2 will be in phase with V2. Let us suppose this to be the I2, and here we didn't consider any resistive drops or reactance drops, therefore E2 will be equal to V2 and V1 is equal to minus E1. It is seen that in ideal transformer, E1 I1 is equal to E2 I2, and if suppose load is connected, then there is an extra current I2 dash, that implies I1 is equal to I0 plus I2 dash is equal to E2 into I2, and neglecting no load current I0, which implies E1 I2 dash is equal to E2 I2. E1 by E2 is equal to I2 by I2 dash, and it is known that E1 by E2 is equal to 1 by K, which is transformation ratio constant K. That implies the relation between I2 and I2 dash is I2 dash is equal to K into I2. Therefore, I2 dash will be equal to I2 if K is equal to 1, and both of these are will be opposite to each other because flux phi 2 dash and phi 2 are opposite to each other. Therefore, I2 dash will be like this for K is equal to 1. And now the resultant current for I0 and I2 dash is I1. And in this phasor diagram, we can also represent the components of no load current IC and I mu. This is the phasor diagram for R load. And now let's draw the phasor diagram for inductive load. For inductive load, if suppose we know that this is the flux phi 1, and let us suppose this is the input voltage V1, and this be the E1, and let this be the E2. And here we consider the step down transformer, so is why E2 is less than E1, and here E2 is equal to V2 because here we didn't consider any resistance drop or leakage reactance drops, so is why E2 is equal to V2. And as here inductive load is considered, therefore to V2 current will be in lag with V2. Let it be lagged by an angle phi 2. And please keep in mind that the load current I2 decides the primary current I1. So as I first draw I2, and then according to that in exactly opposite draw I2 dash, and here considered K is equal to 1, so is why in exactly opposite direction, that is in exactly 180 degrees phase displacement, there is I2 dash, and we know that I0 will be somewhere like this I0, and the resultant will be I1. And you can also represent the no load current components IC and I mu. And now let's draw the phasor diagram for capacitive load, and the same repeats here phi 1, V1, E1, E2, but as here capacitive load 2 voltage current will be in leading. Let this be the E2, let this be the I2, and here we know that here it is equal to V2, so to V2 current I2 will be in leading, let the current be leading by an angle phi 2. And now to represent I2 dash, draw in exactly 180 degrees phase displacement I2 dash, because here we considered K is equal to 1, and we know that I0 will be somewhere here like this by an angle phi 0, and now the resultant of I2 dash and I0 gives you the primary current I1. So these are the phasor diagrams of loaded transformer without the resistance and leakage reactance effects.